Hi guys, we're going to go over the forces revision sheet here as a screencast. So what you can do is fall forward to any of the questions you need to go through and check them against your own working, okay? So here we go. First question was we had a number of different force arrangements and we had to work out the net force in each of these situations. Now notice we've got a little compass rose here so we know which way is north, south, east and west. So the first one, we had two forces acting to the right and one force acting to the left. And so that was a pretty simple situation. So we had one force acting in that direction, and that was 3 newtons. 2 newtons, I beg your pardon. 2 newtons, and the other one was 4 newtons. And here's our object here that they're acting on. And over here we had a force of 3 newtons. And so to work out the net force there, it's going to be 2 plus 4 on this side. That's going to add up to a full force of 6 newtons over here. And we're going to have 3 newtons over here. Sorry about my terrible straight lines. And clearly then this force over here is going to win by 3 newtons. So the net force in this first example was 3 newtons to the right or east, I think we're talking. So the net force will be 3 newtons east. The second example, part B, we've got two forces of 100 newtons acting at 45 degrees. So let's have a closer look at this. So I'll just let you know this is question 1. Okay, so we've got an object and we've got one force acting in that direction with 100 newtons and the other force acting in that direction, that's also 100 newtons. And we know that both of these are at 45 degrees to the easterly direction. Okay, so what we can do, we can actually use components to work out what's going on here. So let's do that. Let's have a look at some components, how we might do this as components. So what I'm going to do, I'm going to break it into components that are actually acting in this direction, in the easterly direction, and look at the northerly components. So this 100 Newton force here will have an easterly component in that direction. This 100 Newton force down in this direction will also have a force component going in that direction. So there's two components in that direction. On the other hand, this 100 Newton force here will have also a component off in that direction, whilst this force will have a component off in that direction. Now, you might be able to see, because of the symmetry of the situation, that these two forces are the same value and they're both exactly the same angle in opposite directions, so to speak. You might be able to see that both of those forces will cancel. They will cancel each other out, leaving behind these two blue components which won't cancel because they're both pointing in the same direction. And so if we're to work out one of those components there, if we can work out that value, then this one here will be the same. And so we'll just add those two together and that will be our net force. So let's go ahead and work it out. And this is going to be a trigonometric problem. So we're going to draw a little triangle here. And that's 45 there. That's the side that we're trying to work out. And we know that that is 100 newtons. And so we want to work out this side here. So I want to do this as a proper trigonometric problem, just for those of you who perhaps need a bit of practice. So the first step is to label our triangle. So here's our angle. This is a right angle here. there's a right angle, and this over here is the hypotenuse, which is the longest side of our right angle triangle. This is our angle, therefore this side is opposite the angle, so that's the opposite, which makes this side here the adjacent. So we're trying to find the adjacent. So we ask ourselves two questions to solve any trigonometric problem. We need to know what are we trying to find, and what side do we know? Well, we know the hypotenuse, and we're trying to find the adjacent. So A and H. And so if we know a little SOHCAHTOA pyramids, SOHCAHTOA, then this one, Ka, is the one that we want. A and H, A and H. And it's going to be a cos problem. So that means, therefore, that the cos of the angle is equal to the adjacent over the hypotenuse. Okay, so cos of the angle equals adjacent over hypotenuse. But we actually want to find the adjacent. That's what we want to find. So if we cover up with our finger, or our big fat thumb, the adjacent, then it's going to be the cos of the angle times the hypotenuse. So the adjacent, which is actually equal to x, which is what we're trying to find, will equal the cos of the angle, and the angle is 45 degrees, multiplied by the hypotenuse, which is 100. And if we work out the cos of 45 degrees, we get 0.707. So that equals 0.707 and times 100, well, that's going to equal 70.7. So that means that one of those blue components is 70.7 newtons. But there's two of them, and they're both pointing in the same direction. And so, finally then, we can say that the net force is going to equal that force in that direction, which is 70.7, plus that force again, 70.7. So that's going to equal 141.4. So it's going to equal 141.4 newtons. And of course, that is to the east. And that's our net force. Right on. Now, let's have a look at question 2. And here we had to determine the magnitude, that should read, of the horizontal components of each of the forces shown in the diagram. So we've got 1, 2, 3 forces. We have to work out the horizontal components. So let's go back here and I'll clear this page. So where are we? Clear. So we're doing question 2 now. And 225, 260 and 290. Okay, let's get the ruler out, shall we? There we go. So the first force is 200 at 25 degrees. Okay, so there's that force, it's 200 newtons, and it's at 25 degrees. What is the horizontal component? Well, the horizontal component is this component here. And so what we need to see, or what we need to do, is complete the right angle triangle. And we have to work out this side. So once again, we're going to label our triangle. So here's our angle. This is the hypotenuse, opposite, adjacent. So once again, we're trying to find the adjacent. So once again, the adjacent will equal the cos of the angle times the hypotenuse. So it's going to be the cos of 25 degrees multiplied by 200. And the cos of 25 degrees is 0.906 times 200, and that will equal 181.26. equals 181.26 newtons. And so that is the value or the size of the horizontal component of that force. The next one is very similar, it's just a different angle, of course. So what we can do is perhaps draw it on the same diagram. So in this case, what we've done, we've increased the angle, and that means the length of the arrow is the same because it's the same size vector, same size force, I should say. So I'll draw it here in a different colour. And that's about the same length, roughly. Now you'll notice here, that's also 200 newtons, but my angle now is 60 degrees. There's my right angle triangle there. You'll notice that the horizontal component's shorter. This component here, in this situation, is going to be shorter. And that's probably what we'll find. So let's work it out. So in this case, it's the adjacent once again. So the adjacent is going to equal the cos of this time 60 degrees times 200. And the cos of 60 degrees is 0.5 times 200. So that will equal 100 newtons. So that force there is 100 newtons. Now the final example is where the force is pointing vertically straight up. In that case, there is no horizontal component. So for part C, the answer would be 0. There is no horizontal component. Okay, so moving on to question 3. Okay, the value of G on Mars is 3.6 newtons per kilogram. What is the weight of a 1400 kilogram car if it were on the surface of Mars? Okay, so 1400 kilogram on Mars, where G equals 3.6. Okay. So question 3. Now we know that the weight force in any situation is equal to the mass of the object multiplied by G, which is the acceleration due to gravity, or the gravitational field strength. And now G on Earth equals 9.8 newtons per kilogram, or if we're writing it as an acceleration figure, it equals 9.8 meters per second squared. That's on Earth. On Mars, it's going to be different. And we're told what the value is on Mars. We're told that it is 3.6. And that's newtons per kilogram. Now what that means, this newtons per kilogram idea means that 1 kilogram of mass will have a weight force of 3.6 newtons. Another way of thinking about that is that if I had 1 kilo, a 1 kilo block that I needed to lift up, I had to try to lift up off the surface of Mars, then I would need to supply a force of 3.6 newtons to lift it. On the other hand, if I had to lift up the same block on the planet Earth, if I lift up the same block on planet Earth, it's got a stronger gravitational field. That's 1 kilo, a 1 kilo block in each case. I'll need to supply 9.8 newtons. So it's harder to lift up a block on Earth than it is on the same block on Mars, because the gravitational field strength is lower on Mars than it is compared to Earth. Okay, so let's work out the weight of our 1400 kilogram car on Mars, and it's going to be the mass of the car, which is 1400, multiplied by G, which is 3.6. And if we work that out, that will equal 5,040 newtons. There you go. So that's the answer to question 3 part A. Now, given a bit of extra information here, the value of G on Venus is 7.2, so it's a bit closer to that of Earth. So what is the mass of the same car? Whoa, look at that. What is the mass of the same car if it were on the surface of Venus? That's a trick question. Mass. It's not asking for the weight, it's asking for the mass. Well, the mass of this block right here is 1 kilogram. This block here is 1 kilogram. Now, the weight, or the force needed to lift up 1 kilogram on each of these planets is different, but the mass doesn't change. So that's something to really be careful of. Mass is constant when you're going from one planet to another. It's the weight that changes, which is the force. The weight of force changes. Sorry about that. Weight force changes. Okay, so the mass of our 1400 kilogram car will be the same whether it's on Mars, Earth or Venus. Because it's not asking for the weight, it's asking for the mass. So the mass will be the same. And in each case it'll be 1400 kilograms. Okay, so look at question 4. Okay, an elevator question. Beautiful. So Julie is in an elevator which is accelerating upward at a rate of 4.9 meters per second squared, and Julie's mass is 72. Okay, determine the value of the weight force. So we've got a couple of questions we need to answer here. So the acceleration is upwards at 4.9 and Julie's mass is 72. So let's draw a picture. And that's always the good thing to do in any of these problems. So we're going to draw a picture. A very simplistic picture. So there's our elevator and there's Julie in our elevator. And the whole elevator is accelerating upwards at 4.9 meters per second squared. Now, two things should be instantly popping into your mind when you see that. Firstly, because there is an acceleration, the speed is not constant, which means there must be a net force. There must be a net force because there's an acceleration. The second thing that must be coming up in your mind is this. The direction of the net force is the same as the direction of the acceleration. Now, someone could have actually created a really difficult problem, or really apparently difficult problem, by doing something like this. The elevator is moving initially downwards with a velocity of, say, 15 meters per second, but it's accelerating upwards. And a lot of people would think, all right, well, it's moving downwards, therefore the net force must be down. No. The net force has nothing to do with the velocity, okay? Just ignore the velocity if you have to determine the direction of the net force. This is solely dictated by the acceleration. So it is acceleration that determines the direction of the net force. Nothing else. Acceleration. Okay, so now that we've perhaps got those few basic ideas out of the way, let's do the calculations. We're accelerating upwards at 4.9 meters per second squared, and Julie's mass is 72 kilos. So we'll just summarise that in our little diagram here. So we know that the mass equals 72 kilograms. Okay, first question I think was, what was the weight? what is the value of the weight force acting on Julie? All right. So for A, we have to work out the weight. Well, the weight is equal to mg. And it's going to be 72 multiplied by, now, if you use 10, then that would be 720 newtons. Or if you use 9.8, that would be 705.6. Okay, that's newtons, by the way. So that's the weight force. The second question was, what is the net force acting on Julie? Okay, well, because we know there's a strong connection between the net force and the acceleration, well, that's the key to working out the net force, because that links straight on to Newton's second law. F net equals ma, Newton's second law. So working out the net force in any situation is actually quite easy if you know the acceleration. So let's go ahead and do it. So the net force is going to be the mass of Julie, which is 72, multiplied by her acceleration, which is 4.9. And if we do that calculation, we get 352.8. 352.8 newtons. That's the net force. Okay. Now, the third part of the question was, what is the value of Julie's normal force? Okay, so what I'm going to do, I'll just clear off some of this to make some space. So I'll clear this area off here, I think. Now, we know, oh, actually, I might actually get rid of that as well. Oh, sorry about that. I'll just try that again. Get rid of that. And I might actually get rid of that. Okay. So we now know that the net force is acting up because the acceleration was acting in that direction. Now, we need to also know that the net force is made up of two real forces. The net force, remember, is just the sum of all the other forces that are actually acting. And in this case, there are two forces that are acting on Julie. There's her weight force, which is acting through her centre of mass, and that's a little centre of mass there, and there's the weight force down. And we worked that out to be 700 and, what was it again? It was 72 times 9.8, we'll go with the 9.8 version, so 705.6. So 705.6 was the weight. The weight is 705.6. Now, we also know that there is a normal force. Now, the normal force is going to be acting up. But because the net force is up, then the normal force is going to be bigger than the weight force. So I'm going to draw it longer than the weight. There we go. So there's our normal force. There it is there. And it's actually acting through at the contact point, which is at Julie's feet. So that messy, long yellow arrow is the normal force. And, okay, so we can now connect the normal, the weight, and the F net with a very simple equation. We know that and I'll do it the rigorous way this time, we know that F net, the net force, is the addition of all the other forces. So there's our net force. It actually equals the normal force plus the weight force, and we'll just call that mg. Now, if we assign our direction, then we will call, say, up positive and down negative. So that means that F net is going to be the normal force, which is positive because it's up, plus negative 705.6 because it's acting down. So that will end up being minus 705.6 newtons. Now we also know that the F net is 352.8. So what's the equation asking us to do? Or what's the question asking us to do? It's asking us to find the normal force. So we need to rearrange N, this equation, to make N the subject. So therefore, if I add the weight force to the other side of the equation, I end up with the normal equals the net force plus, moving this to the other side of the equation, 705.6. And so our normal force is going to be 352.8 plus 705.6. And if we add those two together, that equals 1058.4 newtons. So clearly our normal force is larger than it normally would be if we were just, pardon me, not accelerating at all. So there's the value of our normal force. And the last question was, how many G's is Julie experiencing? Well, G's, if you remember, G's is simply equal to the normal force over the weight force. That's the ratio, or the value of the ratio is N over mg. So it's going to be, and we don't have to worry about the signage here, it's going to be what is it? Yeah, sorry, 1058.4 divided by the weight, which is 705.6. And so it's, sorry, 1058.4 divided by 705.6, and that equals 1.5. So we're talking 1.5 Gs. So there we go, there's the answer to question 4. Okay, moving down to question 5. Okay, we've got a cyclist of mass 60 kilograms is riding up a hill which is inclined at 30 degrees to the horizontal. The mass of the bike is 20 kilograms and there are 4 forces acting on the rider. We've got the weight force, which is acting straight down. There's the weight, 800 newtons. 2, the normal force. Now remember, the normal force is always at right angles to the surface. So here's our surface here of the ramp. So there's our normal acting off in that direction. Friction always acts against the direction of motion. So this person is riding up the hill, so friction must be acting down the hill. And so it's that 10 Newton force there. And finally, there's a driving force, which is what's propelling the cyclist up the ramp. So that's basically due to her pedaling and the work that she's doing. So that's the situation we're talking about. And the first question is, calculate the component of the weight force which is trying to cause the bike to roll back down the hill. So how much of this weight force is causing the bike to, or trying to cause the bike to roll down the hill? Another way of thinking about it would be, how much of the weight force does a rider have to work against to ride up this ramp? So let's go ahead and do this. Very first step is to draw an accurate picture. It doesn't have to be to scale, but at least a nice clear diagram. So that's what I'm going to do. So there's my ramp and there's my horizontal. Okay, now I'm not going to bother drawing a rider, I'm just going to draw a blob. Okay, so just got a blob. Okay, that can be the rider. Right? Doesn't matter what it is, it's just, okay, there's our object. So let's mark in the forces as we need them. Now in this particular problem, the first part of the problem is to do with the weight. So I'm just going to mark in the weight to begin with. And acting, there it is there. There's our weight force. down. And we know that that equaled 800 newtons, I think, from memory. Let me just check that. It's 800 newtons. And the angle is 30 degrees. So this angle here is 30 degrees. Now, we have to work out how much of this weight is acting down the ramp. So what we need to do is break our weight into, you guessed it, components. And one component will be parallel with the ramp. So I'll just draw a line there that's parallel. I'll just draw a little dotted line, actually. So there. And the other component will be at right angles to the ramp. So we're talking something like that. Okay. So, the component that we want is that component there. That's the component of the force, of the weight force acting down the ramp. So let's go ahead and work that out. Now remember, let's go back to that setting. Remember that whatever angle is here, whatever the angle is in there, that's the same as the angle in here, okay? So that angle in there is also going to be 30 degrees. So if we work this out, this force here, using our, once again, we're going to be using trigonometry. This is our angle, this is the opposite, this is the hypotenuse. We're trying to find the opposite. So in this case, the opposite is going to be the sine of 30 degrees. So it'll be the sine of 30 multiplied by the hypotenuse, which is 800 newtons. So now the sine of 30 degrees is 0.5, so that actually equals 400 newtons. So that force there is 400 newtons. Okay, so that's the amount of our weight force that's actually acting down the ramp, making it hard to ride up the hill. And the steeper our hill, the greater the component of our weight that would be acting down the ramp, and therefore the more difficult it is would be to pedal up the hill, which sort of makes sense. So let's look at question part B. Now, calculate the normal force acting on the rider bike system. Okay. So remember, there's our normal force there. So let's have a look at our normal force. Okay, so I'll reintroduce my ruler. Oh, there you go. How handy is that? Now, the normal force, remember, acts at right angles to the surface. Now, because there is nothing in this problem to suggest that the bike is going to accelerate off the ramp or they're going to accelerate through the ramp into the ground. The motion and the acceleration of our bike is up the ramp in this direction. So we're assuming, well, we're not assuming anything, we know that the motion of the bike will be, if they're able to overcome friction, it'll be up this way. And if it was down this way, we're in this plane. So that's the direction the thing is accelerating or decelerating in. So there is no acceleration in this direction. There's no acceleration in this perpendicular direction, which means the net forces in this direction must cancel out to zero. So that means that our normal force, which is this force, must be the same as this component of the weight force. So that's the way we're going to work out our normal, by working out this side here, then that's going to be the same as this. So if we work that out, if this was the sine of the 30 times 800, then this is going to be cos of 30 times 800. So to work out this side, it's going to be cos 30 times 800. and the cos of 30 degrees is 0.866, so equals 0.866 times 800, and that equals 692.8 or thereabouts, 692.8 newtons. Okay, so that means that this component here is 692.8, which means that our normal force must be 692.8 newtons. Okay, so let's move on to the next part of the question. Part C. If the rider is riding at a constant velocity up the hill, what is the value of the driving force? Okay, constant velocity. I'll do that again. Constant velocity. One more time. Constant velocity. No words are necessary there because you know what that means. It means that acceleration equals 0. So the bike is not accelerating up or down the ramp. They might be moving up the ramp, but that's irrelevant. Remember we said that net force has nothing to do with velocity. It's all to do with acceleration. So constant velocity means acceleration equals 0. So, and because we know acceleration is 0, that means that something else equals 0. Yes, that's it. Net force is equal to 0. So, we can now draw in the remaining forces, and because we now know that the net force is 0, we know that all the forces must add up to 0. So let's see how we go. So let's have another look at our little problem here. So it's 10 newtons down the ramp, and this driving force is up the ramp. Okay. So we know, I'll draw this in a different colour, I think. I'll go with a nice purpley type shade. I'll try that. Okay. So we've got 10 newtons acting, and this is not drawn to scale, I might add. There's our friction, 10 newtons. And we've got some sort of a driving force. And we might make that yellow. Okay? Right, so there's our driving force. But hang on, don't forget about this. So we can actually take this vector and move it up here to show that it's acting on, this is acting on the rider. So I'll go back to my orange colour and bring my ruler back, and what I will do is this. I'll just draw the box again. Very quickly. So there's our box without the ramp. We know that there's a 10 Newton force of friction acting on it that way. We know that there's some sort of a driving force acting this way. But we also know there's the component of gravity acting down the ramp, acting that direction too. That's 400 newtons in that direction. So down the ramp, acting down the ramp, we've got a total of 400 plus 10. So there's our mass, or the bike. So there's a force of 410 acting down the ramp. Now we've already worked out that the normal and these forces here cancel. So we've got 410 down the ramp, and we know that there's some sort of driving force. But we also know that the net force must add up to 0. So whatever the driving force is, it must balance this force, so it must also be 410 newtons. So the driving force, this driving force, is 410 newtons. Because it had to not only combat the 10 newtons of friction, it had to also combat the 400 newtons of, which is the component of weight acting down the ramp. So, B, C, if the rider is acting constantly, what is the value of the net force? Well, we've already answered that question. The value of the net force is 0. And that is a direct result. That is a direct result of that. Okay? So the answer to question D is the net force is 0. Okay. Righto, question 6. 2 trolleys. Ah, beautiful. I love these problems. 2 toy trolleys are connected by a piece of string. There's a string there. And they're pulled along by a spring balance. So this is sort of like the prac that we did, except here the person's pulling along with their hand and a spring balance. We had our pulley going, we had our string going over a pulley, and a little weight was pulling it along. But pretty similar sort of idea. And the reading on the balance is 14 newtons. So this reading here must be reading 14 newtons. The front trolley has a mass of 4 kilos, and the rear trolley has a mass of 3 kilos. And we're assuming that the bench is smooth, horizontal, and no friction. What is the acceleration of the trolleys? Okay, so what we're going to do is, as normal, we're going to draw a picture of this situation first. So let's do that. So we've got, this is question 6. We've got one trolley. And we've got a second trolley. And they're connected by a piece of string. And that in turn is being pulled along by a spring balance. Okay. So let's put in the data that we know. We know that this trolley has a mass of 3 kilograms. And this one has a mass of 4 kilograms. And we know that what the force that's pulling all of this along, all of it, not just this trolley, but all of it, is a force of 14 newtons. Okay, that's the force of the spring balance. So we know that there is a force of 14 newtons pulling this along. And actually we'll draw the force a different colour, I think. So it's accelerating that direction, and I like using the ruler, so I think I'll use it. So there's a force of 14 newtons pulling everything along. So because this trolley is connected to this trolley, then as far as the person here pulling everything along, as far as they're concerned, they're dragging along 7 kilograms. That's what they're going to experience. So this 14 newtons is trying to accelerate 7 kilograms of mass. So to work out the acceleration of our trolley, which is part A of our question, whoops, sorry about that, the acceleration of our trolley, now what's important here is the acceleration of this trolley, whatever that is going to be acceleration of the whole system. So everything will be accelerating at the same rate because it's all connected. So using Newton's second law, which of course is the acceleration is equal to the net force divided by the mass, then we can quite easily work it out. Now, there's no friction, so there is no friction, and there's no other forces other than the normal forces and the weight forces. Now they'll be acting up and down, and they won't have anything to do with the motion of the trolley. Okay, we're going to pause our video here, and in the next segment we will actually continue.